In this video, I'm going to go over example 8.3 out of the Electrodynamics book by Griffiths, 4th edition. In previous video, we have now derived terms for the energy density, the momentum density, and now we want to apply that to a specific case. So the case we want to consider is I've got a coaxial cable, which is essentially made out of two cylinders. Like so. The inner cylinder has a radius, so the inner radius is A. The outer radius is B, right here. It has an overall length of L, like so. And now what we're going to do is we are going to hook this up to a battery. So imagine that I connect the outer cylinder to a battery and then hook it up to a resistor, and then I hook that up to the inner cylinder. The battery has a potential of V. The resistor has a value of R. So what's going to happen is that battery is now going to push charge through the coaxial cable, and a current is now going to flow down the inner conductor and then wrap around on the outer conductor, like so. Okay, so what we want to do is determine what is the momentum in the field. So not the momentum that's going to be flowing through the boundary, but what's the momentum inside the fields in this particular situation. So, okay, what is the momentum in the fields? Okay. So I said that there's a current that's flowing on the inner and the outer conductors. I can now think about how much charge there is over the surface areas of these conductors. So let's say that the inner carries a charge density of lambda. So that's charge per length. Okay. So now if we were to apply Gauss's law to this particular situation, then we would get an electric field that is 1 over 2 pi epsilon naught lambda over the radius s in the radial direction. So essentially what we have is I built a Gaussian surface over top of this, basically surrounded the inner cylinder by another imaginary cylinder, and the radius s is that distance from the center to the Gaussian surface right here. For the magnetic field, we can do apply Ampere's law and build an Amperian loop which wraps around the inner cylinder, like so. Okay. So, I'm not going to show it, but we've done it before to show that for a cylinder, Gauss's law would give you an electric field which is radial outward, which makes sense. Electric field is pointing from the inner cylinder to the outer cylinder. That's where the potential difference is across those two cylinders. The magnetic field is mu0 I divided by 2 pi s. So again, I get that from Ampere's law, only considering a loop that's surrounding the inner cylinder, and the directionality of it is going to be tangential to that Amperian loop. So it's going to be in the phi direction. Okay, so if we now calculate the pointing vector, that would be E cross B divided by mu naught, which is then lambda I. The mu's cancel, and so then I get 4 pi squared epsilon naught s squared, and then I have an s cross phi. Okay. Now in cylindrical coordinates, my s, which is radial, my phi, which is now pointing tangential to the cylinder, is going to produce a z component, basically. So s crossed into phi is going to be equal to z, like so. So again, if I draw this out, I would get phi pointing in this direction, s pointing in this direction, therefore z is going to be pointing perpendicular to both that plane right there. Okay, so now we've got the pointing vector, so I'll write it again as lambda I over 4 pi squared epsilon naught s squared in the z direction. Okay, so we want to get the momentum. But first, let's consider the energy. The energy in the fields, or the power at least, is going to be the integral of the pointing vector in the area over the area. Now, in this case, it should be a closed surface. However, the pointing vector only points in the z direction. So in terms of our cylinder, if we look at the area vectors of our cylinder, then the pointing vector is only pointing along the z-axis. So we don't have to consider that boundary. And so what we get is, for power, just S dotted into A, which is lambda I over 4 pi squared epsilon naught, the integral from radius A to B, 2 pi from the d phi, s ds over s squared. So in the end, I just need to take the integral of s 1 over s, which is the natural log, which in the end gives me lambda I over 4 pi squared epsilon naught 2 pi the natural log of b over a. So I can cancel out these, and I get lambda I over 2 pi epsilon naught the natural log of b over a. So that's the energy, or the power, I should say. That's the power. If I now look at the momentum, which is what I wanted to do in the beginning, then the momentum, it would be mu 0 epsilon naught the integral of s over the volume. Now the volume in cylindrical coordinates would be 2 pi L s ds. So 2 pi comes from the phi direction, L comes from the z direction. And so s, the pointing vector s, is only dependent on the radial direction s. So therefore, if I put it all together, I get a momentum which is mu 0 epsilon naught, the integral from a to b, lambda I over 4 pi squared epsilon naught s squared in the z direction 2 pi L s ds. Okay, so now we can start canceling stuff and get rid of one of the pi's. That becomes a 2, and get rid of one of the s's. So in the end, what I get is mu 0, epsilon naught cancels. So I get mu 0 lambda L I in the z direction over 2 pi, and now integrate from a to b of 1 over s ds. So again, that gives me the natural log, and so what I get is mu 0 lambda L I in the z direction over 2 pi, the natural log of b over a. Okay, so that is basically the answer. Okay, but if I compare it to the power that we calculated before, the power was lambda I over 2 pi epsilon naught, the natural log of b over a, which we know that the power being consumed by that resistor is equal to the voltage times the current. So now I can replace everything in this equation that I had with VI. So the momentum, written in a little cleaner form, is VI times the length times mu 0, and now I get an extra epsilon naught from the power. So epsilon naught, mu 0 epsilon naught VIL, in the z direction. Okay, so essentially everything in here, so this stuff is all VI. So I just have to replace that in the momentum equation above, right here, with VI times epsilon naught. Okay, so that makes it even easier equation to see. Now let's say that we don't want to work with mu 0 or epsilon 0. We can rewrite them. So if you remember that mu 0 epsilon 0 is equal to 1 over c squared, where c is the speed of light. So therefore, in this case, the momentum in the fields in this coaxial cable is VIL over c squared in the z direction, like so.